So hey guys, I'm Jiří, I guess you know me, and today I'll be presenting about cybersecurity. Basically my introduction as a layman into the security for other laymans. If you expect some like very mathematical details, you will be disappointed. But if you want to understand the global picture and some applications of that, then I guess you should be okay. So this is stolen from Wikipedia. So the cybersecurity is meant to protect information disclosure from information disclosure. It's also meant to protect the hardware and software and disruption of the services. We will be focusing in this presentation on the first point, so about protection of the data, where the key role plays, cryptography plays the key role. So what is cryptography? Cryptography is science basically about making digital things secret, so protecting them from being read by third parties, and there we use encryption. It also helps us identify the origin, basically ensure the authenticity of some data, and also integrity, meaning that the data weren't tampered with while being transmitted. So, and for that we have digital signature. So today I'm going to give you a very quick introduction, a very high-level introduction into encryption and digital signature. I'm going to show you which tools you can use to actually implement these in the stack that we know, and also show a few recipes on how to use the low-level bits to actually accomplish some more complicated scenarios. So let's start with encryption. So as I said, encryption is there to protect data from being read by a third party. So if you're transmitting data or storing data somewhere, it shouldn't be possible for a third party to just come and read the data because they are encrypted. As I mentioned already, there are two types of encryption, two basic types. One is the encryption for transport or transmission of data. So basically, on one side, you encrypt the data, and then you forward the data encrypt the data to somewhere, and that recipient decrypts the data and interprets them. The other one is at rest encryption. So whenever you want to store some data, you don't want the data to be stored in plain text so that anybody could access and read the data. You encrypt that, and while reading, you decrypt that. Easy peasy. There are different kinds of encryption, or basically cryptography in general. There is symmetric cryptography, asymmetric cryptography, and also elliptic curve, which is basically asymmetric with some special properties. So we'll go over these now. So symmetric cryptography. It's symmetric because it uses the same key on both the sender and the recipient side, or writer and reader. So basically you have a key with which you encrypt the data, and the same key you are afterwards used for decrypting. It can be used for basically unlimited amount of data. It's very handy for at-rest encryption because usually the one who writes the data and reads the data is the same person or same entity, basically same server could be. So it holds the key. And the most famous currently used algorithm is AES, Advanced Encryption Standard. So how this work? I will just go through it again. So we have a message and we have a key. We use the key to protect the message. We encrypt it, then we can store it somewhere. And then while reading it, we use the same key to decrypt the message. With asymmetric encryption, it goes a little bit more interesting. We don't have a single key, we have pair of keys, private and public. And one of these keys can be used for encryption, and the other one can be used for decryption only. One is used for encryption, one is used for decryption. The public one is used for encryption, the private one is used for decryption, meaning that anybody who receives the public key can encrypt the message and send it to a single entity who holds the private key and can decrypt the data with it. There are some limitations to this. One of them is like the length of the message that you can actually encrypt, and because of the nature of not disclosing your secret key, like in the case of symmetric encryption, you can use it very easily for transport encryption, because you can just send your public key to the sender, and then the sender can encrypt the message and send it to you, and only you can read it. So you're not disclosing any secrets when you're providing the public key, because it is public. The most famous algorithm used for this is RSA. It's pretty old, and the acronym stands for the names of the gentleman that invented it. So let's just have an example again. So we have a message and we have a recipient. This is home is basically a recipient. It's some kind of a closed server. And the recipient generates the key pair. So it generates a private key and the public key. The public key can usually be derived from the private key. And what it does, it sends the public key to the sender. So the sender has the ability to encrypt the message with the public key, then send it over an insecure channel to the recipient, and the recipient can use their private key to decipher the message and interpret it. Because each of these have some drawbacks and some benefits, usually there are scenarios where you want to combine both, and so you can use the asymmetric nature to actually transfer data, but also to use the symmetric thing for encrypting large sets of data. So then you usually use an additional key, like you have the asymmetric key pair and an additional key that you use for encrypting the data, and that's something that is usually used for. Actually, it's always used for SSL or TSL, and it looks like this. So you again have private and public key generated by the recipient. Then on the sender side, you randomly create an encryption key for symmetric encryption, and then you use that key to protect the message. So you encrypt the message with this random key, basically, and you can send it to the recipient. Of course, the recipient cannot interpret the message, cannot decrypt it, because they don't have the blue key, right? The symmetric one. So what do? We use the public key of the recipient to also encrypt the blue key, and then pass this encrypted blue key together with the message or through other channels, whatever. But in the end, the recipient can use their private key to decipher the encrypted blue key, this symmetric one, and once they have it, they can easily decrypt the message itself. So this is how you combine the two approaches and mitigate the problems that each of them has. Then there is this special kind of cryptography, elliptic curve cryptography. You can find out why it's called like that on the internet. I didn't fully understand it. I don't really intend to fully understand it. So if you want, you can feel free to look it up. But the point is that there are no random keys in here. So it basically, you can imagine it as a previous scenario where we combine the stuff. But this elliptic curve cryptography does it for you, because you don't need to randomly generate a key, and you don't need to exchange this randomly generated key. So what it does is that you can generate, each of the sides generates a pair of the keys, right? So the recipient generates private key and the public key, and the sender does the same thing. The fun thing is that each combination of public and private yields the same shared secret. So basically, if I combine private key of A and public key of B, I get some value. And if I combine public key of A with private key of B, I get the same value. And this same value can be used as an encryption key for symmetric cryptography. Basically, it represents this blue one that we showed earlier. So how does it work in here? Again, there needs to be a transfer of the public key, which is there always. So the sender needs to have the public key of the recipient and its own private key. By combining this together, they can generate or calculate shared secret, which is basically a value. And usually by some hashing and some additional things, you get the actual symmetric key, which then you can use to encrypt the message. And you pass the message to the recipient. So then what? Along with the message, you also need to transfer your own public key, because that's the only way how you can make the recipient to actually decipher the message, because they then combine those two keys, their own private and your as a sender's public key, and they generate a shared secret, which is the same as generated from the other two keys. So you can then again derive the symmetric key and decipher the message. So that's how it works. Both sides need to follow the same properties of the curve. And if you imagine the elliptic curve somehow, then it has a lot of properties, and you need to pre-agree on which of these we'll be using. So that's required. And there are also some like standardized libraries of these properties. So they have names, and they are supported in major frameworks, major libraries. So this kind of works. And the main algorithm here used is so-called elliptic curve Diffie-Hellman. So that was about encryption. Now digital signature. So digital signature is not used to protect the data. It's used to protect the integrity and authenticity of the data. So you know, digital signatures from like if you are signing some documents. So basically, what it does, it creates a signature, which is like a couple of bytes, well, more than a couple, that somehow represents both the document that you are signing and your own identity somehow. And then if you want to verify if the recipient or whoever wants to verify the signature, they can if they know some information about you. Again, there can be symmetric and asymmetric digital signature based on what types of cryptography are you using. So we'll start with the symmetric one, which is much simpler. So again, like with everything symmetric, you have a shared secret which both the sides have. So the one who signs and the one who verifies. That's the problem. So usually you do this only in the case when the same entity is signing and verifying. So imagine a server issuing an access token. So they use a secret and sign it, and then the same server then receiving the access token and verifying it. So they can just use the shared secret, and they don't need to use any kind of complicated asymmetric process. So, and then we basically calculate the signature using hashes, and that's what the HMAC does. So how does it work? You have the secret, and from that you derive two keys, secret 1, secret 2, and you somehow do hashing on multiple levels. That's a protection against so-called message length extension vector attack. It doesn't really matter that much, but what's the important message here is that basically you combine the secret and the message itself, and you hash it together. So that's how you create the signature. And the other end does the very same thing. They take the message, they take the secret, they hash it all together, and they get the same hash. And if the hash matches, then the signature is correct, and the origin and integrity was verified. Usually, you don't really hash the message itself because you don't really sign the message itself because the message can be super long. But prior to that, you also hash the data, so you get a very strictly limited buffer, and you use that buffer then to sign it. So all the digital signature things actually also rely on good enough hashing function. So in the asymmetric digital signature, it works kind of similar, but it also uses hashes, but it uses the properties of the asymmetric cryptography. So you have the pair of keys, private and public again. There is a difference now that the private is used for signing because that's yours, personal thing, right? So only you should be able to sign. So you have your private key, you sign with the private key, and the public key can then verify the signature. Again, RSA is used for that. So again, you have this. You have the pair of keys. You have the message that you want to sign. You first hash the message because you don't want to sign like thousands of bytes and whatever and megabytes because RSA and asymmetric encryption in general is very limited to the message length as we discussed already. And then what you do is you use your private key to decrypt the hash. Why I'm saying decrypt? Because if you remember what we said about the asymmetric encryption, we are using public key to encrypt and the private key to decrypt, and that's how it works as well in here. But you can imagine that we would use the same operation as for decrypting to somehow randomize and hide and obfuscate the hash, and then we will use the opposite operation, meaning encryption, to actually get back the plain text version. So that's what is used here. So we are using private key to manipulate the hash, basically like if we are decrypting it, and generate the signature. Then we have the signature, and we pass the signature along with the message to the recipient. Recipient then uses their public key to kind of encrypt the signature, which results in the plain text hash again. So then the only remaining part is to use the same hashing function to hash the actual message that came and compare the hashes. If they match, the signature was verified, and integrity and authenticity is guaranteed. So the main application that you would probably came across already for signature are the various tokens, right? So JSON Web Token, for example, that's basically a JSON object which you serialize to two parts. So there are actually two objects, one for header, one for payload, and then you use either HMAC or RSA to sign the token, and you append the signature to that huge string, which you can then take and pass along with every request in the authorization header or wherever. And the server is then able to verify the signature. And once it does so, it can trust all the information which is in the payload. This is very useful when you don't want to repeat queries to the database, for example, checking if the user has the permissions to perform something, right? So what you do during the authentication phase, you basically authenticate the user, you authorize them to perform certain actions, and those permissions that you found for the user, you inject them into the JSON Web Token. You basically generate the JWT, you sign it, then you forward it to the client. The client keeps it, sends it with the next request. And when it comes to your server again, you just verify that the signature matches, and you can trust everything that is inside the JWT. So you don't need to do any kind of database lookups again, find out the permissions or whatever. It's already there. Of course, there are caveats like that the JWT access token needs to have a very limited validity, because otherwise you wouldn't be able to revoke some accesses for the user, because it's all baked into the JSON. Anyway, so now about some support from the stack that we are used to use. So Node.js has a native crypto module which supports most of the algorithms that you can think about out of the box. So that's probably the stuff you should look for. And also there is a plain JS implementation called crypto.js, which probably supports more. So if you fail to find a particular algorithm in the crypto module, by the way, the crypto module also doesn't. I think it doesn't really specify which. Oh, it does. Okay, doesn't matter. If you don't find the stuff that you are looking for in the native module, you can always fall back to the JavaScript implementation. Okay, in the browser, they recently introduced a web crypto API, which is available in this crypto subtool. I wasn't really able to find out why it's called subtool, probably because because they implemented some very low level features there. Anyway, it's again built into the browser, so it's pretty quick and it's sufficient for a lot of operations. What they claim is that the standard doesn't really tell you which ciphers and which algorithms are implemented there, so you need to kind of rely that the browser implement the basic ones. And again, you can use the crypto.js as a replacement because it works both on Node.js and the browser. So there, like, you can somehow polyfill it or check whether the native support is there. If not, you can fall back to crypto.js. Crypto.js is definitely much slower than the built-in API. Mobile devices is where it starts to be interesting. So both Android and iOS, they offer some key stores where you can either store your keys and use them and retrieve them. But the most important interesting thing is that it allows you to generate a key within the key store and never reveal it to either party, to you, to other applications, to the system, anywhere, because you don't really need the private key unless you are decrypting or signing, and that's what the key store does for you. So instead of retrieving the key from the key store and then passing it to a crypto library that actually performs the operations, key store itself is able to do those operations. So you just tell them, okay, I have a key somewhere there. Maybe it has some kind of alias or ID, and you'll tell them, use this key to encrypt this data. Sorry, to decrypt this data, or use this key to sign this message. So it takes the data, pushes it to the system, and the system then does it for you and spits out the result. But it never reveals the private key. And you can also ask it to reveal the public key, because the public key should be forwarded somewhere else. So that's very useful because it increases the security. Also, usage of the keys or access to the keys basically can be protected by biometrics on the phone. So you can enforce fingerprints or face ID to actually unlock the key. In Android, it's Android, so it depends on the vendor and on the version as well. But on some of the phones, actually the key store can be hardware backed as well. So there is a special hardware that handles this. We will get to it in the iOS part. Android supports, the key store supports symmetric encryption and asymmetric encryption. I guess they also support the elliptic curve, but I didn't really look. And on iOS is where it starts. Where it's again a little bit more interesting because they use a fully separate and dedicated chip on their hardware where all this happens. And they claim that also if you are able to root the system or basically compromise the kernel, you shouldn't be able to access the keys at all because they are in that specific hardware. And they support the elliptic curve keys there. And of course, they also support, but indirectly, it's not super in the hardware, the symmetric encryption for actually encrypting the data. Because as you saw with plain elliptic curve, you cannot really do any encryption or decryption because it only generates the shared secret. So that's about mobile phones. And then if you want to be really paranoid in your environment, you might want to think about using HSM, which is hardware security module. It's basically very similar to what iOS does or Apple does on their phones. but it's a standalone device. It's either a PCI card or a USB device or something connected to the network. And again, it has the keys baked somewhere very deep on the hardware, and it doesn't allow anybody to retrieve the keys unless they really damage the device. So they would be able to do it only if they physically have the device and if they disassemble it to pieces and stuff like that. So again, it performs the operations internally. So you just instruct it to do something. They internally use the keys, but they never reveal that. Usually release of the key, basically doing the operation, signing or decrypting, is authorized by a signed request. So you have some kind of other certificate that you can use on your own server to sign a request, and then send the signed request to hardware, to this HSM module, and only then it can actually do something with the key. If you don't want to go through this hell yourself, to attaching and making sure that it works, then you can also use cloud provided HSMs. Like AWS provides one. I also saw that Google and Azure does the same thing, very similar thing. So that's also pretty interesting. Anyway, now we're getting to the recipes. So how to use what we have learned right now. So one of the very basic applications of digital signature is two-factor authentication. So you know the two-factor authentication, like that you accept some request on your phone when you're logging into Google, to GitHub or whatever. So how does it work? In ideal scenario, you have a phone on which you generate, again, an asymmetric key pair, ideally in this secure enclave or wherever, in some kind of a key store. And then you push the public key as part of a device registration to your server. So your server has the device linked with the public key. And then when there is an authentication request, we basically just push a challenge code. Anything. Challenge code can really be anything. It usually is generated from something real. Sometimes it can be a random number, but it depends on the level of security that you actually want. But you push the challenge code to the device, to the mobile phone. Then you use the private key in that mobile phone to actually sign that challenge code. And then you push the signature back to the server, and the server uses the public key to verify that the signature matches. And that's how they know that it was actually you, or basically your device, who authorized this challenge. Nobody else could ever return the same challenge signature, because the challenge code is always unique, right? For each login, they generate a new challenge code. So even if somebody eavesdrops the communication, they won't ever be able to submit a signed signature for any other new challenge code. So that's a very straightforward and useful application of digital signature. So now another scenario. Let's say we have a server where we need to persist some sensitive information about the user. All right, so the first thing that strikes us is probably we shouldn't do it in plain text, so we should probably encrypt it somehow. Okay, it's at rest encryption, so we would probably use symmetric encryption. So we would have an env variable somewhere on the server, keeping a secret, and then we use the secret to encrypt the data in the database and to decipher them as well. Yes, but then it means that you or anybody who actually gets access to your database and to your system, to your cloud, basically, have the possibility to decipher the user data, right, and read it and misuse them. So maybe we could protect it by the device of the user. So imagine the scenario where we have this device enrolled already from the previous example. So we have a device where we have the private key. somewhere safely secured in the key store, and we have a server where we already have the public key. So now, let's say there's an incoming piece of data which we want to store in the database. So what we do, we don't want to encrypt it with the public key itself, because first of all, it's not super easy. Second of all, if we do that, then we would need to push all the encrypted data to the device in order to be decrypted, right? Which is probably not a good idea if you have a document of like 20 megabytes. Then sending it to the mobile device each time you want to access it is not really cool. And also, that means you send it encrypted, but it goes back unencrypted, which is also not super secure. Anyway, so we have the incoming data, and what we do, we generate a symmetric key, a random one. And we use the symmetric key to protect the document. So we encrypt the document with this symmetric key. Okay, so now we have it protected. So what do we do with the symmetric key? We cannot save it into our database, because then in the database there will be encrypted data and also the key to decrypt the data, which is not something what we want, right? So what we do, we encrypt the symmetric key with the public key of the device, and we store both in a database. So we have the encrypted data and the key that accesses it, which is protected by the device. So next time we want to access the data, we just need to push this encrypted key to the device. The device uses their private key to decrypt this symmetric key, and it passes it back to our server. And our server has a temporary way of how to decipher the data. So they can decrypt it, they can send it somewhere, use it, whatever, and then they can again throw away the symmetric key, and the data in the database are still safe. The benefit is also that you can manipulate with the blue key. You can theoretically decrypt it and encrypt it with something else. So maybe you can also switch the device, right? So if we would protect the whole document with the device, we would need to decipher the whole document. If you have a server where you have thousands of documents, it would be a pain in the ass. So if we are migrating to a new device, for example, what we could do, we just send all the blue keys. We just send all the blue keys to the device. We decipher them, and we can to the original device, and we decipher them, and then we can encrypt them with the public key of the new device, and that's how we handle the easily migration to a new phone. So that's about this. And then there is a special case of basically something that we just discussed, and something that might not be super obvious, and that's why it's pretty handy to show it here. It didn't fix the typo. Anyway. Imagine that we are doing some kind of a checkout process in e-commerce system where we need to communicate with the payment gateway, and the payment gateway might send us some sensitive data like I don't know, name of the person who's actually buying it, or a credit card details, something that we want to show on the receipt maybe. And so we don't want to store this in plain text, right? So again, we want to have some kind of an encryption, and we are super paranoid, so we don't want to have our data encrypted with a key that we own. So what do? We can create a key which will protect this session basically. And where do we create it? Well, in the browser, because the browser will be open throughout the whole checkout process. So you use this web crypto API to generate a pair of keys. Then you somehow initialize the session by pushing the public key to the server. And in that moment, the server is able to encrypt any kind of incoming data with this specific key. So when it happens, for example, the payment gateway gives us a callback with some information, and we want to store it, we will do the same thing as we did previously. So again, we will generate a random key. We will use that random key to protect the data, and we will use the public key of the browser, not the device, to protect this key. Afterwards, when we want to finalize, we can store that, of course, everything in the database. it can live there for the whole session. It can be database, it can be Redis, it can be memory, whatever, doesn't really matter. And when we are about to finalize the session, we again push this encrypted key back to the browser. The browser decrypts it, sends it back in plain text, and on the server, we can decrypt the data, process it, generate PDF, invoice, receipt, whatever, and just throw it away. So that's how you can keep your data secure, even from asynchronous sources. Okay, last one. It's basically about delegating access to somebody else. So imagine that we have this protected document in our database with the key that, just a second, I need to organize my thoughts. Yeah. Okay. So we have this blue key which protects the document, right? And so what we could do in order to delegate access to the document, we could just send this blue key to anybody, and that anybody would then be able to read the data if they access our database or if they send it through our API. There is a little bit of drawback here, because if you do that, the person has an eternal access to the data unless you delete them from the database. So what we could do instead, we generate yet another key, and we protect the blue key with this yet another key, right? And then we can store this in the database, of course, and then we can send this yet another key to the person. So it works the same way. If the person wants to retrieve the data, they send this, I don't know what's the color, the yet another key to our server through an API. We use it to decipher the blue key, and the blue key then deciphers the data and can send the data back to the user or perform anything with the data what we want. The benefit of this yet another key is that everything we need to do to revoke the access from this person is to delete this blue protected key from the database. And theoretically, if we combine these together, there could be multiple of these protected keys, of these delegated keys. So we could granularly revoke access to some of the actors, basically, and not specifically removing the data from the database. So that's the last thing that I wanted to show, I think. Yeah. So that's it.